At e-PLASCOM, we study plastics with a clear goal to reduce their environmental impact. We focus on using recycled or renewable raw materials and on sustainable manufacturing methods.
Our group works on natural or biodegradable polymers. We study their thermal, mechanical and rheological properties. We also work on eco-design, new processing methods for thermoplastics and rubbers, and also for components weight reduction. Finally, we tackle the challenge of plastic waste, recycling, revalorization, and also turning residues into valuable materials.
Through our research and industrial collaborations, we aim to design smarter, greener, and more sustainable polymer materials for industry and society.
One of our promising solutions is developing a research line dedicated to the design of elastocaloric rubber materials for clean, efficient, gas-free cooling technologies. Today, nearly 20% of global electricity consumption is used for cooling and refrigeration. Traditional cooling relies on refrigerant gases such as hydrofluorocarbons, which have global warming potentials up to more than 3,000 times higher than CO2. Although international agreements such like the Kigali Amendment aims to phase out these gases, the world's demand for cooling continues to rise sharply, and it is mostly driven by urbanization, electronics, and climate change itself. This creates a major problem. First, the cooling demand is increasing faster than we can decarbonize. Second, the current refrigeration technologies are approaching the limit of performance and sustainability. And third, the industries, the household, and emerging economies are heavily dependent on these systems. So we urgently need solid-state, energy-efficient and eco-friendly alternatives that can replace polluting refrigerants and enable cooling solutions with low cost, low environmental impact and high scalability. Our solution is based on the elastocaloric effect in rubber, a phenomenon in which rubber heats when it's stretched and cools down when released, without the use of any type of gases or harmful chemicals. We engineer rubber composites capable of ±10 degrees of temperature changes with potential up to -14 degrees below room temperature. Our materials use recovered rubber from end-of-life tires combined with renewable fillers such like nanocellulose, making the technology sustainable and circular. The formulation and processing are protected in our patented elastocaloric rubber composition, and unlike shape memory alloys, caloric materials, our rubbers are low-cost, lightweight, highly deformable, easy to process and scalable for industrial production. Our solution can deliver cleaner cooling for homes, public spaces and transport, directly supporting the global effort to decarbonize a fast-growing energy demand. Beyond these environmental benefits, this technology can also be applied to create miniaturized, lightweight and flexible cooling systems for critical applications such like electronics, wearable, sensors, establishing then a new platform for thermal technologies. This positions elastocaloric rubbers as one of the most promising pathways for solid-state cooling technologies. They are safe, affordable and eco-friendly. From 2025 through 2026, we will focus on materials optimization to enhance performance, durability and energy efficiency. We will then move straight into prototype development or at least proof of concept in 2026 and 2027, creating working demonstrators of small-scale technology and heating elements. And finally, from 2027 to 2028, we will focus on industrial integration, collaborating with cooling sector and materials partners to scale up production and integrate our elastocaloric rubbers into real-world applications. We invite collaborators from companies interested in sustainable cooling, institutions supporting energy and climate innovations, and the public stakeholders to follow and share our progress with elastocaloric rubbers for cleaner and more efficient cooling.